technical manager here at my HCT. And Dan's not going to be there. I think he's stuck in a meeting right now, so I'll be covering for him today. Quick overview of structural analysis toolkit. I know you've seen it before, but just scope the demo with these slides and showcase all the different capabilities. I know we'll focus mostly on the stress processor, and that demo use a random vibration processor as an example. But the purpose of the tool is twofold. One is to provide a user-friendly environment for running Sol 111 in an XNASRAN. So either a random vibration or a signed vibration analysis. It leverages kind of the same backbone of NXNASRAN, but differently in a way that you can trim down solution time by about 75% compared to traditional NASRAN in some cases. Okay, so it's not unusual to see this amount of time saving. But the toolkit can also be used for post-processing to extract various quantities in an automated way. So we're looking at modal processor, the stress, the mass, or the GPF and elemental force processors. These outputs can be visualized both graphically in FEMAP, right, as contour plots, but also as Excel results, like probably the ones you've been familiar with or that you've seen in the past. The software supports FEMAP, but it also supports NX or SimCenter 3D, just an FYI. Now I'm talking about the stress processor here, so there is an interface that's directly embedded in NX. It's also compatible on Linux, Windows, and also parallelizable. Okay. I'm just going to go through the random vibration process because that's the one we're going to cover today. So multiple benefits. Just in terms of setting up the simulation, you'll see it's easy and it's fast. I know you can run a solution 111 in FEMAP, but with the SA toolkit, it's a bit more intuitive, all right, and it's less prone to error. But I think most importantly is the computation time. So for large models, let's say 1 million nodes, so if we have 3D elements, about 3 million degrees of freedom, you can run solution 111 in 120 minutes. And for large tent meshes, if you were to run that in FEMAP, it would take quite a large amount of time. Okay. Same thing goes for signed vibration processor. I'll skip that one, but I think the one you're interested here might be the modal processor, which generates metrics for looking at modal effective masses and fractions. You can also identify local modes that have small modal effective masses yet result in a higher response. So there's quite a few tools that can be used within the SA toolkit that generates both Excel results, but also UNV results that you can import in FEMAP. Okay, and one of them is the typical stress processor. So I think this is one of the most useful tools of the toolkit, really to be able to extract the margin of safeties for different failure theories. Von Mises works for laminate, to look at first ply failure, for instance, or honeycomb sandwich instabilities. And just to note that any time you run either a random or a signed vibration processor, the stress processor is automatically run afterwards. Okay, so you do not need to run this guy and then this guy after the other. It's all in one. But you can use this stress processor on literally any OP2 you generate. And the output will be both in an Excel sheet, but also as a result files you can import in FEMAP to look at contours.
Well, I assume you're getting all the stress components out of element types, or?
Sorry, come again?
I assume you can get all the different components out of the stress output. You're just listing like a beam element here. Within that beam element, are you covering everything?
Mm-hmm. Yeah, exactly. So what you'll get in the UI is not only the margin of safeties, but you also get the peak values, so the 3 RMS values that you can plot for all of the elements.
So
you can either,
if you're recovering forces, is there a place that's set up then to calculate the stresses, where each user will then define what the stress calculation is for that set of forces?
So you're asking if you can. You have to repeat the question, please.
So like for beams recovering stresses, you're using the corner points or whatever corner points, stress recovery points, and I'm assuming that's initially what you're calculating the margin from on this. But you may also, a lot of times, you keep the forces, not look at the stress recovery points, and then you go in and calculate your margins based on the forces in that element.
Yeah. Okay, I understand.
Yeah.
So you also track the forces such that you can, within the spreadsheet, write your own margin calculation that then gets reported in a table like this.
Absolutely, yes.
Yeah. Sorry, go ahead.
Yep, sorry, there's a bit of delay here with the GoToMeeting. But yes, so you can do that, and then that's where the grid point, the GPF, and the element force processor comes into play.
Okay.
Okay.
Yep, so typically when we
find ourselves using stress processor more for shells and the element force processor for beams and springs.
So just to be clear, like if you've got a C-quad element, you can get out a max shear and a principal stress and a von Mises stress.
Yep, you get the peak values for them. Yep.
Yeah.
So when it's calculating the margin, can you show the detail of how it's got that margin what it's using for that margin calculation?
Yep, we have I can pull up the equation afterwards. We have in the documentation we have the equation that's used for calculating, the max von the von Mies, or sometimes you want to use the worst case stress. So there's also an equation for that. So both are. I'll pull it up afterwards, but the description is in the documentation for the equation. If you want to back calculate it yourself, you can do so. Either by looking at different stress components, or if you're looking at beams or C bushes when modeling bolts, you can export here the element force processors and the GPFs.
So somewhere you've got a table of what you're setting up as allowables for these materials and stuff like that.
Yep. And I'll show that in the demo.
Okay.
Sounds good?
Yep.
All right. Okay. Yep. Let me quickly wrap that up then. So that's the stress processor is the most used tool. There's a mass processor as well that can help you tune your model if you do a dynamic analysis. Some people use it. Some people just do it by themselves on an Excel sheet. But then there's the GPF and the the element force processor that can be used to extract more forces at grid points, MPC, SPCs, and also force along certain coordinate systems if you're modeling bolts. So we use that a lot, and copy those forces on our own Excel sheet to extract our own bolts margin of safeties. All right, this being said, I'll jump into the demo. So what I have here is a satellite dish model in FEMAP. We ran initially a solution 103 analysis. So we have those results here for all the different modes. And the reason why we have that solution 103 is because we'll want to run a random analysis using the SA Toolkit. Okay. So I'll just pull that up. So you'll see here the SA Toolkit can be can be either embedded here. So you might, if you have the SA Toolkit embedded in your software, you'll see a small icon here called SA Toolkit. Otherwise, what you'll end up having is a standalone SA Toolkit here that can lock into FEMAP. Okay, so we can either lock in or we can pull it out like this. Now it's like it's standalone. Okay, so I'm just going to put it down there. Put it back right here. Okay, so what we're going to do first, we'll point to an OP2. So this is the OP2 model analysis that we ran previously. What we can do is set an output project location. So this will be the location where all the files will be saved. We got a few groups in our model that were predefined in FEMAP. Okay, so we can either export those groups into a UNV in FEMAP, or if it's embedded in FEMAP, what you can do is you can just directly import it from active FEMAP model.
So,
so this will read.
Our menu is going to be coming from NX and ideas. So
okay. Yep. So we can either import those groups universal or using for a Nastran BDF or that file.
Okay. Universal file. Okay.
All right. In terms of analysis, at this point, no, because it's only a modal analysis, we might want to run either a modal summary, which is the modal processor, or we can run a random analysis here in this case. And you guys are familiar with how to proceed with the random analysis setup in FEMAP. Now, what I'll show you is how you can do it in the Toolkit, real quick. Right. So first step, we pick a base acceleration. All right. So by default, it's going to pick the SPC node, which sits at the bottom 1, 2, 3, 4, 5, 6. That's the one. Can define acceleration or different subcases in different directions. Because we're in FEMAP, we need to use a proper scale factor. And then when we define is a PSD here. So you can import a file. So here I think I create a small PSD that goes from 10 to 1,000 hertz. Goes point 0.002 to 1.1 Gs. Okay.
What's your scale factor?
Scale factors to make sure that we're working here in metric.
Okay.
Okay, so 1G, 9810 millimeters squared per second. That's the input PSDs. Next, what we're defining is the parameters where to evaluate that frequency. Okay, so because we've run a SOL 103, and this case runs here a SOL 111, what we'll make sure is to use all the modes involved in it. Okay, so we'll just pick here all the modes. We can specify basic damping. In this case, we'll leave it as is. That's 2% damping. The analysis parameters, this will define how we calculate our peak values. Okay, so default is 3 for three standard deviations. So these are going to be 3 times your RMS. It's going to be your peak value. We have different integration schemes to integrate the PSD. Okay, the hybrid method is fast and accurate. No, in FEMAP, typically what you need to define is some frequency values of some FREC card, FREC 2, FREC 3, FREC 1, to define where to integrate your PSD. The more points you have, the better, the more accurate your results will be. If you don't have enough points, you might overestimate your your peak response. One of the benefits in the Toolkit with the random processor is that you don't need to define those FRECs. Okay, so the integration will be done automatically. And then in terms of solution setup, we're almost done. All that needs to be defined now are the stress cases. So in other words, what do you want to look at? And for which element do you want to output margin of safeties? And this is what we call stress case definition. Okay. Just to note here, if I create this here, you'll see that we can look at margins of safeties based on the exact von Mises. Okay. When I say exact von Mises, these are the phase consistent von Mises. Or you can just have a look at worst case, and you'll see we have 2 different equations for each. Or look at use the exact only when you are below a certain cutoff when printing your margin of safeties. Okay, so in this case, we'll look at von Mises. We'll select our groups. So for which groups do you want to export those margin of safety? So why not take a bunch of them like this? Those are read directly from FEMAP or imported from UNV if you work with NX. Allowable stress. So you were asking that question here. This is where you set it up. You can set it up for everything at once or per group. So in this case, I could do here just put aluminum and just have this allowable stress factor, maximum margin for sprint. Click OK, and there you go. So you can have as many stress cases as you want.
That's always based on von Mises. Can you pick the stress component? Can you pick the stress component, or is it just always based on von Mises?
It's only based on von Mises for this.
Okay.
So for composite, in core, what do you do? Just von Mises?
No, so here that would be, if you look at the failure mode here, you can look at yield, ultimate, and then you'll see instability. This is where you're going to put your, this is going to be for laminate. Okay, there's a few options. I can pull up the documentation afterwards. You have a few a few failure modules you can pick from. Okay.
But it's still a von Mises
Uh,
stress that it's
yes, I think they are for laminates. I think they are depending on the failure theory. There are other parameters that you need to define. Um, but I have to admit, I'm not. I can't recall. No, I'll have to look back and see what additional parameters you can put for them. Okay. Yep. I'll just put myself a note here for laminates. Uh, I'll go in and pull those different options you can for input. All right. So we've got a few stress case here. So let's click OK. And then in terms of output, this is where you'll define, how you want to see those results. So typical. If we look at margin of safeties, we can look only, through an Excel sheet. This is probably what you're familiar with. But now what we have is a UNV or a neutral file. So this will be the output in FEMAP. Okay, so you can add it to the scenarios. We can look at accelerations. In this case, you either have the choice to look at peak values with 3RMS, or you can look at the whole PSD across frequency. So we can try that. This will generate plots of acceleration at key locations, either for all nodes. It's going to be a bit cumbersome. So what we'll do is we'll just look at our acceleration group node, which are key nodes spread out through the model, including the excitation node. Okay, so technically this is a good sanity check where you look if the excitation is equal to the response at this particular point. Okay, so we can add acceleration here. We can also add peak values for accelerations, right? So instead of just having the PSD, let's pick it for all elements, and perhaps displacements. Okay, so the same, like this. Right, so you can define as many outputs as you want. Here you can see there's quite a few.
element forces.
Yeah, sorry, I'm going too fast. So GPFs and joints, composite failure matrix if you have laminates, GPFs, stresses, strains, all of those are available as output. Okay. Okay. So now at this point, you can always go back, save the file. So essentially, this will generate a DAT file that you can reuse. So let me just put it up here. So this input file here that you can edit, and those can be saved and reused over time. Okay, this is a summary of everything that was defined in the input.
So it looks like a Nastran.
It's similar to Nastran.
It's not actually going to go to Nastran. Is that correct?
Did you ask if it's not going to go to Nastran?
Correct.
Yeah, no. So this does not use NX Nastran.
Right. It's just formatted like a Nastran deck in terms of appearance, but it's really just what you guys are post-processing on the SOL 103 results to create the random environment. And it's
you are correct.
Looking to us because we're used to Nastran cards. Is that?
You are correct. Yep. And the format of this file is available in the documentation, so you can technically write this whole format from scratch or slightly edit it or change the ranges.
Yeah.
Okay.
Yeah. So if you want to change the group or make your own group outside of any of the processors, you would just type it in. Yeah.
Yep. This guy here. Yep.
And we kind of see here on as well. It's a similar type of make list.
Right, and we've defined the stress cases manually at this point, but the stress cases are nothing else than just this, right? So what you'll do is just copy a stress case or write it from scratch and just add your own allowables for each. So again, can be done inside or outside.
So can you read in multiple inputs to create multiple cases, or is it just do you work on one input file at a time?
I believe there's an include command in this format, so you can include other files if you have multiple text files. So the main one has to be .inp. The other ones I think can be others. I'll just have to verify afterwards on my end if the command is include, like in Nastran, or if it's something else.
So like if you want to do X, Y, Z all at the same time, you might have an X input file, a Y input file, and a Z input file, or do you just do them all?
You mean like if you want to run different expectations for each, or?
If you want to run all three at the same time.
Yeah, three directions at once.
You can do it within the same file. So if I look back here, I'm going to go here, my random analysis, basic acceleration. You can define more than one subcase and have X, Y, or Z.
Okay. Okay. So we have this in a home-built MATLAB routine we call FRAP. And,
okay.
So we're just tracking it in our heads as you go through.
No, that makes sense. I understand.
And it's for the same reason that running in Navstran was just too slow to run Solution 111.
Right. Especially when you get to those big models above 1,000,000 degrees of freedom, it's Solution 111 is slow. It's slow.
Yeah.
Okay. All right. So this particular model, if we look at, let me just click OK. If you look at it, it's about 35,000 nodes. So all 2Ds times 6, about 180,000 degrees of freedom. Right. At the end of the day, that's it. That's all we had to do. That's all we had to set up before running. So let's click start. We have some information going on here, and see. I think I left the Excel sheet open on my end. Okay, hold on a second. Bring this up. It just ran it this morning, and it did take 3 seconds. So let's just see here what's going on. Okay, let's stop it for a second. Let me close the Excel sheet and rerun it again. So, okay, let's see here. Pop frequencies, pop modal damping. Now this parameters. Okay. All right. Okay, let me run it again.
Very one.
Okay. Apologies here. I think I'm running into a small technical issue. I'll be right.
Right. It's what happens for every demo, right?
Yeah. Yeah. It runs once, and then when it's showtime.
Yeah, or that never happens.
All right. Okay. I think I got this one here.
You just need to go find somebody else to come in and tell you, that they did the same thing you just did. It worked.
Okay. I'll look what's up with this one right now. I think it's stuck with Excel, so it's having it's essentially the solution is done. Okay.
Like
so
the file
after
looks like Excel or something already, and it's not allowing you to write to it, or it's not recognizing that.
Yeah, so right now I think it's the problem with my Excel, with the Excel communication. It's stuck at the Excel file and can't open it. So typically, I ran it I ran it multiple times. The random analysis takes less than 3 seconds to run, 480,000 degrees of freedom, and then everything here is written. And what you can see here, these are all the files that are written out. Okay,
Okay.
it
So
looks
you
like
can take
it's
that XML file and just plop it into Excel, probably, right?
exactly. So let me just look here if the Excel is complete on this part.
I like how the words are in French in Excel, the file type.
Yeah. Okay, so let me just see if it's finished. No, there's an issue with my Excel communication right now. Anyhow, yeah, I'll show you the main outputs of this kind of analysis. So, there's a bunch of files here that are written out. The main one, so if we look at the HTML right here, you'll see we did request for acceleration at a bunch of nodes. Not sure if you recall that. So when we do this, we do get the PSDs for all of the requested node in that acceleration group. So if I go back to FEMAP, I already requested this here, right? Oh,
Yeah.
there you go, it's finished. Okay. So all the PSDs are shown here. And if we
So
look
how
at
do
the
you
input node,
overlay these? You highlight all of them at once?
if you want to overlay them, we have both the PNGs, but also the data in the Excel sheet. Okay, so if we look at this, um, the acceleration.xls, gonna go in this one here. Oh, yeah, that's the reason. So the reason why it took so long is because it was already open. Now it just asked me to remove it. Okay, all right. So if we look at the acceleration, those are all the accelerations for all the nodes. Okay, so you can plot them if you wish.
So that's
Okay, we also
RMS.
have. Okay, so let's see, maybe.
That's not actually the frequency.
Oh wait, let's see here. I know this is what happened. So if we go in random analysis, output request, when I specified my acceleration output, you see I did not request for the Excel file. Right.
Right. So if you took the HTML file though and just threw it into Excel, it would fit. Correct?
Actually, that's something I've never tried.
HEA's
So
format does that. They write out the XML file and you just drop it onto Excel and it pops
okay,
up.
let me give it
First
a try. Something I did not know. Let's see. Yep, I'm not getting too much.
No? Okay. So it's an HTML,
Yeah, so,
not an XML. Yeah.
yeah. So I guess to achieve what you want, Steve, in this case, you just have to activate the Excel output right there. That will generate an Excel sheet with the same plots, but also with the data that comes with it. Okay. So that's for the graphs. Let me just close that up here. So here you can see that the input is it's the same as the output. Close this. It's a temp file. And if you look at the summary file, okay, so that enabled the macro, and I think you're familiar with this format, right? That's what you've seen a few years ago?
I can't even remember. It's been 15 years.
Okay,
Since
15
Louis
years. Okay. So in all of this, you get the summary of what's been run. You've got those displacements, peak response that we've requested for all the nodes. So those are the 3 RMS values. Same thing we did for accelerations and the margin of safeties in this case. So only margin of safeties that were under 100%. That was our cutoff criteria. So if we go back here, random sub analysis, we did specifically ask for any margin of safeties that are under 100%. This you can change it. Okay, this could have been, very high to output everything, but at the end of the day, these are the only elements that were, in that stress case that held these particular margin of safeties, and this is the through RMS von Mises stress. Now we can also import those results in FEMAP, so it's not just Excel. I'm just gonna make some room here. Cancel, close this. So this you can undock it, just put it aside. Now what you can do is import the file. Okay, so we're gonna import a FEMAP neutral. And if you look at the output, you get one neutral file here that you can import. So that neutral file contains the RMS values, so and the margin of safeties. Okay. So click OK. Excuse me. So we'll go in contours, look at our results. Contour, there we go. And then our output results is going to show up here. You see LC1 peak values. This is the new output set that's been created. And now you can look at some of it. So we got, the margin of safeties. In this case, all of it is activated, although we've only requested for so much. Okay, so we can look, for instance, at acceleration everywhere, and you get the values here. And you can cycle through everything. So those are margin of safeties.
Yeah.
Okay. So at the end of the day, this is a summary of FEMAP's capabilities. If I go back to the folder where all the files were generated, what do we have? We have the FEMAP model, the mod FEM, OP2. Um, then this is national files, and then get all of those available. Okay, it's a lot, but essentially what you need is in. Yes.
Yeah, and then are we going to look at forces?
You want to look at the element forces?
Stress
Let's see
process
if we can.
for
Yep. So we'll run it. Yeah, we can run it here. So
So I think this gets us starting with a picture, but what we really, the goal of something like this would be, it gives us a common tool to process results, whether we're using BMAP, NX, Patran, whatever the user is.
okay.
Our primary goal is to get everybody in NX and having a consistent processing tool, and we can either develop it ourselves or we can see what's available. And,
Okay.
and we dominantly, we look at the forces and the stresses, and we aren't looking at things based on margin until after we've looked at the forces and stresses. And we like to be able to, if you go to the, so it's all the way from coupled loads analysis results, combining with acoustic, looking at random, looking at sine, looking at quasi-static load cases where we've got 96 load cases run and we need to find out what's the max. And we know FEMAP identifies that quickly, and I think you can identify that quickly as well. But the gist of, this is an initial get acquainted, and then to go back and say, okay, divorce ourselves from using FEMAP. I don't really want to add any more FEMAP licenses to get users. I want them in NX running their data or ideas, and then using a toolkit, whether it's this toolkit or whatever, that everybody can look at the data the same way, get their plots out, get their overlays, and everybody knows what to look for then in this toolkit, because if you're looking at somebody else's results, you know what you're familiar with that. It's not somebody else's VLOOKUPs generating a bunch of plots and stuff.
Okay. So just to make sure I understand right now, in terms of what you'd like to see on top of this, is you'd like to be able to look at the forces in the elements, so either 2D elements or 1D elements, and be able to do the post processing yourself, or work it out in any customized way. Is that right?
Yeah, I mean your stress margins, once you get familiar with it, they're probably fine. But we're going to want to look at the forces individually as well.
Okay.
And then develop and understand where your stress margins are coming from, because at some point it looks like too much of a black box for the stress margins, and that's the bottom line. So the user's got to be able to easily manipulate what's being done to calculate those margins, because they're going to get into an SER and you're going to show it. You're going to show a table of the results, the max loads for each one of those.
I understand. So what I propose is, I think what would add the most value in terms of showing you what those specific capabilities. Perhaps what I could do is gather some of the documents we have specifically for that processor.
Okay.
Perhaps put something up together that showcase specifically what you're requesting for, and also gathering the proper documentation that lists the equations used for calculating the stress output.
Yeah, and where it's editable, and does it come up in a, is it in a spreadsheet as well, where you're saying, okay, this is the element type, this is the margin calc.
Right. Okay. Yep. I think I think the best way here would be, let me go on my end, grab those materials, and I'll send them over. I think that'd be best.
And even the margin calc probably isn't the driver for what we want. The driver we want is just for processing large amounts of data consistently, that the tool, develops that. We can write our own OP2 reader and stuff like that, but, and I can use IMAT to do that or whatever for that, but it just becomes a maintenance thing and a user thing and a license thing. And, I'm trying to find something that eases our pain but gets us consistent and affordable.
Right. Let me throw in an idea here. Would it make sense to try to apply our stress processor on any of your OP2s that you're currently using, but takes a long time to post-process?
It will eventually, yeah. But I think right now we just want to see how things operate independent of BMAP, just with the OP2 and what we would get. In terms of, multiple load cases, and we'll go from there.
Yeah. All right, sounds good. So I think the next steps then, let me gather the material for you. Make sure that the capabilities you see in FEMAP for processing forces looks fine, and then maybe afterwards what we can set up is perhaps a trial with you guys where you can use the tool with our help and try to post process some of those big OP2s you're facing, and look at how much time it takes. Look at the outputs.
Okay.
Does that make sense?
Yeah. Why don't you send Marilyn and I an email and we'll get with you on. And you were going to send some PDFs of the post-processor as well. And we'll go from there.
Excellent.
No rush on this. We're just trying to keep our eyes open.
Sounds good.
And then,
all right.
And do you have any plans of embedding? I mean, NX already has a